Good day to all. I hope you had a good little break and that I'm finding you in good spirits, in good health, and ready to continue our calculus course that we actually left a little while back with an unfinished business with area between curves. So what I want to do with you today in this short video is to solve yet another problem on how to find the area of a certain region bounded by certain curves. So here's example 3, 2.5 stars to complete the section. So challenging, but not incredibly difficult either. And it goes like this. Find the area of the region bounded by the graphs of y is equal to root x, y is equal to minus x plus 6, and y is equal to 0. So step 0 is going to be to actually do what? What do we need to do to begin this problem? Well, if you remember, the formula for the area between curves is the integral of y high, y low. So the best way to figure out what is the y high and the y low is to actually sketch the graph of the region. So basically, this is what we're going to do. Sketch the region. So y, x, very nice straight line. So those two curves are not terribly difficult to sketch. Y is equal to root x, well known. Y is equal to root x. The second one, y is equal to minus x plus 6. What is that? X to the 1. It is a straight line. You got it. So straight line, couple of points. Choose them well. X-intercept and y-intercept are always good choices. So if x is 0, y is 6. And if y is 0, x is 6. Let's put the 6 over here. My scaling is not very accurate, but it'll do. It's a sketch. It's not a precise graph. So roughly it does something like this. And the region is not quite yet bounded until we incorporate the third constraint, y is equal to 0, which is the x-axis. And now we have this region, and we have to find that area. Very good. So step 1, let us complete the graph by finding the missing information in this graph, which would be what? What is missing in this graph? Aha! If you answered the intersection point, you're right. So we'd like to know where that is. So intersection point or points, we don't know. Points are usually found by putting y is equal to y or x is equal to x. So for the sake of the argument, let's put y is equal to y, which will give us what? Root x is equal to minus x plus 6. How do you solve an equation with a root? Well, yes, you square both sides. So the root of x squared is x minus x plus 6 squared. All right, square this, bring everything to one side. Here's what you're going to get. X squared minus 13x plus 36 is equal to 0. You can fill in the algebra here, it's easy. And now I want to solve this quadratic equation. So of course I can use the quadratic equation, or I can find product sum two numbers whose product is 36 and whose sum is minus 13. If you are thinking of minus 4 and minus 9, well, we are thinking about the same thing. That'll work, which will give us 4 and 9. Lovely. Now 4 and 9, this is 6, so clearly this is most likely 4 comma something. And if I want to know that something, I can put x is equal to 4 in one of the two equations. So say the first one, root of 4 is dos. You may wonder, how come we got the other answer, x is equal to 9? And the answer to this is when we actually squared both sides of the equation, we basically, instead of using the curve y is equal to root x, we use the curve x is equal to y squared, which, as you know, is the sideways parabola that will go this way and eventually catch up with the line where, you guessed it, at 9. Since this is outside of our region, we don't care, and we basically have the point of intersection we needed, which lead us to step 2. Step 2, set up the integral. So I'm going to do a little bit of a zoom in like I like to do. So my region looks like this with my key points. And then I'm going to do what I usually do, because the formula for the area is y high minus y low. So let me draw a vertical little tiny skinny rectangle on the left side. And let me identify the y high and the y low. Y high, I am on that portion of the curve. That curve is root x. Here I'm on the x-axis. Good. Now, if I draw another rectangle to the right side of the region, also has a y high, also has a y low. But you will notice that this time the y high lies on the line, not anymore on the square root. So the y high on the line, minus x plus 6. And the y low on the x-axis still at 0. So what we see here, guys, is that we basically have two regions, because the y high is not the same throughout the entire region, meaning we are going to have to divide this into two different regions. Here comes region 1, here comes region 2. And the area of region 1 is the area of y high minus y low. The y high in region 1 we have established to be root x. The y low, 0. Now we got to tell the bounds of this integral. The further to the left x is 0. The further to the right x is 4. And then it stops at region 1. What is that? This is the integral of x to the 1/2, which we know to be x to the 1/2 plus 1 over 1/2 plus 1. So that's 2/3 x to the 3/2 between 0 and 4. FTC part 2. Put in the 4 and put in the 0. 4 to the 3/2 is 8 times 2/3. 16 over 3 is actually the area of the first region. The area of the second region is also y high minus y low, but a different y high and the same y low. So this time I'm going to have minus x plus 6 dx. And this region 2 begins when x is 4 and stops when x is 6. So what is that? This is minus x squared over 2 plus 6x between 4 and 6. What will this be? Let's put in the 6, so that's minus 18 plus 36. Let's put in the 4. That's minus 8 plus 24. You can do the math. That's equal to 2. And if you were thinking of finding the area of region 2 using the area of a triangle, you are absolutely correct. That can be done also very easily, and you'll get the same answer. Clearly, you'll get 2. So that the total area will be the area of region 1 plus the area of region 2. So we're talking 16 over 3 plus 2. We're talking 22 over 3 square units. Lovely. Well, that took us like a solid 10 minutes. Now I'm actually wondering if there's a way to do this same problem in a faster and perhaps more efficient fashion? And the answer is, of course, it can be done. Let's consider this alternate approach. Alternate approach, probably better seen if I do another zoom in. And this time, if you allow me, I will actually draw not a vertical rectangle, but rather a horizontal rectangle right here, which will have not a y high nor a y low, but rather, what will it have? An x to the right and an x to the left. In that case, the x to the right lies on the line. What is the x when I am on the line? What is the x when I am on the line? This is the equation of the line. You want to know what x is, you have to isolate it. Isolate x from this equation, you're going to get 6 minus y. That's what you're going to get. What is x to the left? You are on the square root. If you want to know what x is on the square root, you're going to have to isolate x from y is equal to root x, which means squaring both sides. So root x squared is x, y squared is y squared. And what is interesting here is to notice that wherever you draw your horizontal rectangle, you're always going to have the same x right, the same x right, and the same x left everywhere. X left is always on the root, x right is always on the line, which is very interesting because it gives us a chance to figure out the area using only one integral. This time, we're not using y high, y low, we're using x right, x left. And of course, that will be a dy integral. So we said x right is 6 minus y, x left is y squared, and then we have to tell the integral y runs from where to where. Now you remember the first zoom in, or the original graph, the lowest y is the x-axis, which is 0, and the highest y you will find is that point where y is 2. So that integral shall run from 0 to 2. Not a difficult integral at all. 6y minus y squared over 2 minus y3 over 3 between 0 and 2. Lovely. So let's put that in. What do we got? 6 times 2 minus 2 squared over 2 minus 2 cubed over 3 minus a big bunch of zeros. That'll be 12 minus 4 over 2 is 2 minus 8 thirds. That's 10 minus 8 thirds. That's 30 minus 8. Yay, 22 over 3 square units. And of course, that is the same answer as we have obtained previously, except it is done in a considerable number of lesser steps. So that concludes this example. The next time we'll meet, we'll be starting our next section in the course Cal 2, which will be volumes of revolution. Okay, I'll see you soon. Take care.